we can start. Yes.
So it doesn't matter if I have little gaps.
It doesn't matter at all.
They should edit out quite easily.
Yes, quite easily. Yes.
Okay.
Yes. Now please, as two camera are now rolling.
Okay. Well, this talk is about metal bonding. The bonding between atoms that hold a piece of metal together at the atomic level. It's a simplified version which I wrote for my family and friends. I mean, the full paper is, I don't know, 15 pages of theoretical physics, but this is just about 3 pages of simple explanation of the paper. The full reference to the paper it's published. It was published at the beginning of last year, but that's 2024 last year, yes, and by myself and C.U. Chen, a graduate student who was helping me with things, in Journal of Physics Condensed Matter, volume 36, paper 353002, published in 2024. There are two strange things about metal bonding. The first is that if you have a grain of sand or sugar or a crystal of salt and you just hit it with a hammer, it'll crush into a powder. But a metal doesn't do that. The metal just flattens, and that's different, it's unusual. The bond between neighbouring atoms is a covalent bond, the same as in hydrogen bond H2 or oxygen O2 or water H2O, or indeed all the molecules that make up our bodies. So it's not that they're different. It's the how they work together that is different. Somehow the atoms of a metal hold strongly together, but they care far less about how they are arranged in their crystal structure or whatever with respect to their neighbours. That's why if you hit it, the atoms shift around, but they're still close together because the metal doesn't expand or contract. It still has the same volume as before. It's just that it's changed. In chemistry, we learn about how two neighbouring atoms join together to form a covalent bond between them, such as the oxygen we breathe and the water that we've just mentioned. The other strange thing about metals is that if we make a picture of how we think the bonds are, just between atoms, sort of a classical kind of picture, we would have all these atoms and place the electrons between them, making the bonds. But what that would be strange is that we only have 3 electrons in aluminium and 12 neighbours. And in sodium, as a more extreme example, we only have one electron per atom and 12 or 14 neighbors. How can one electron per atom form enough bonding to hold all this together? That is the second thing that is strange about metals. A short piece of mathematics in the main paper shows that in quantum mechanics, that in quantum mechanics it's different. This physical picture that I described of the electron sort of between the atoms, that's correct. But in classical physics, it would be that in one instant, and then another instant the electrons would have moved, and so they would be moving about, and on average it would be everywhere, but it would be moving. The electrons are entities, and they would be moving like that. And in quantum mechanics that is different, because the quantum mechanical thing is the electron is a wave function that is spread out, and so the electron is indeed everywhere all the time, and it's the ground state, as we call it, the basic state of the system, is then a mixture of all possible pictures that you can draw at the same time all together. It was pointed out by Pauling already in 1938 that if you look between two atoms, the covalent bond looks just like any other covalent bond. But it's this totality that is different, with only one electron in sodium or 3 electrons per atom in aluminium, that somehow spread themselves around in a quantum kind of way that then holds everything together. A short piece of mathematics applied to the quantum mechanics of this shows that the bonding of an atom is not to its neighbor individually, but as a covalent cluster bond to its cluster of covalent of surrounding atoms as a whole. That's different from this and that and the other. It's one cluster bond to all its neighbors simultaneously, and its bond strength is proportional to the square root of the number of neighbors for each such bonding electron. Yes, C is the total coordination number, we call it, of neighbors around the atom that we're discussing. It is totally an inherent quantum effect that all of these pictures are included in the ground state meaning lowest energy state in quantum mechanics. They're not sort of alternatives in time. There's no classical counterpart to this in classical physics, as underlined, emphasized in a paper by Schrödinger in 1935 discussing this. Now, a lot of things immediately follow. First of all, they explain why metals have close-packed crystal structures. I mean, you can have crystal structures with an atom having 4 neighbors or 6 or something, but in metals they all have 12 or 14 neighbors, and that is because they form these cluster bonds, and the cluster bonds they like to have as big a clusters as possible, and so they have a shell around the atom enclosing it. That's one of the basic things. Secondly, we note what a huge multiplicative effect this enhancement by the square root of the coordination number. I mentioned that the energy of the bond is proportional to the square root of the coordination number for each electron. So each covalent bond has this square root of the coordination number as a multiplicative factor. And that's a lot. I mean, 12 neighbours or 14 is the norm for metals, and the square root of 12 is 3.46, and so you're multiplying the strength of the bond that you think the bond might have by 3.46 to make it this cluster bond and bond to the cluster of neighbours as a whole. The next thing that it explains is the easy structural phase transitions. I mean that usually we think of phasic transitions classically that, well, they have one structure, and at another temperature or pressure they may have another structure, but it's a big disruption to change from one structure to another. In metals this is not so. I mean, the important thing is the cluster, and the cluster is still there. It may be just atoms have moved slightly, but even that may not be so. I mean, face-centered cubic and hexagonal close pack are made up out of the same clusters, but stacked differently. And so the phase transitions between one and the other as a function of temperature or pressure is very common amongst metals. Fourth effect that I've noted is there was a couple of metallurgists called Dorr and Basques in 1983. Now this is a long time later. I mean, they found that just they were modelers, putting in atomic models to understand dislocations and things in metals, complicated effects in metals, because at that time people were studying nuclear power, and you have all these nuclear nuclear particles being expelled with big force, and they cause damage in the shells that hold the plutonium or uranium together. And so there's a lot of radiation damage, and it's very important to understand that. Another problem that a puzzle that it really cleared up was the energy of a vacancy. I mean, a vacancy is just if an atom is missing. And if you think of 12 neighbours, well, you've broken 12 bonds if you take an atom out. Then when you put it on the surface, you can't destroy atoms. So what you do is, the way physics works, is you take the atom out and then you add it just as an extra atom on the surface. Well, on the average, with 12 neighbours, every atom has 6, you're making 6 new bonds each time you add an atom. So you've taken out 12 and you've got 6 back. So that you might expect the, so you've lost 6. Well, when you just build up a solid from atoms, you're adding 6 and 6 and 6 to build up the whole. And so you might expect the energy of a vacancy to equal the opposite of the binding energy of the material. So in other words, yes, the vacancy is the same as taking away an atom. Well, it isn't. It's half that. And the half is, well, you have to do some bit of complicated algebra. It's not really terribly complicated, but it comes from the square root. The square root means to the power of 1/2. And so it's from that this factor of a half comes in. The paper, it was published at the beginning of 2024, also has a couple of interesting applications to chemistry. The first of these is catalysis. Now, my simple picture is not discussing any particular catalytic reaction, but it does discuss something that contributes. It's a grossly oversimplified system. Let us consider a monovalent metal, just one electron per atom, and let us consider a pair molecule of that same atom element. And then we can consider the element for the molecule, the pair, first as a molecule in the vacuum above the surface, and then we think of it on the surface, and we're concerned with the energy of the molecule dividing. Well, in the vapor phase, it's obvious, it just divides. I mean, we have one electron from each atom in our simple picture, so it's two bonding electrons. On the surface, it's different because the two atoms, the molecule sits on the surface and it's attached to the surface, but they're now moving apart but still attached to the surface. And it's that difference that makes a big difference to the energetics. If the coordination of the material that it's on, it's the coordination, the extra coordination at the surface. So you have an atom on the surface sitting on a if we think of just a simple cubic structure, it would the atom that it's sitting on is enhanced from having 4 neighbours to now having 5 neighbours to now having its total 6, which is what the simple cubic structure would have. And so it's a change in the bonding of the surface atoms of the material from 5 to 6. Well, that gives it a better, that is extra bonding from the point of view of the metal that it's sitting on. But that is retained when the two atoms on the surface, the molecule, move apart. And so instead of the atoms on the surface, instead of having lost their total bonding, they've reduced it from 1 to something like the difference between 5 and 6. Now, if you look at square roots, the difference between 6 and 5 is quite small. The difference between 1 and 0 of the molecule in the vacuum, in the gaseous phase, is big. One bond broken, well, it's 2 up and down spin, and the same is applied on the surface. But it's 1 compared with the difference between 6 and 5. And the difference, in fact, between the square root of 6 and the square root of 5. And you can work that out, and that's, of course, quite a small quantity. And so the presence of sitting on a surface makes the breaking open of the bond of the molecule from the vapor is much reduced. And I mean, chemists may be surprised that one can make a sort of a general theory of catalysis, because I think chemists tend to think of each chemical reaction as different. And that they're of course correct. But running through any such calculation that they might make, there would be this theme, there would be this fact of quantum mechanics, that the energy for pulling them apart on the surface is a lot less than pulling them apart in the gas phase. and that will remain. That's where this is where a physicist thinks in terms of these simple models. But I mean, chemistry was my first love at school, and so I keep that orientation. Now we come to a second application to chemistry, and that is the benzene molecule. This is benzene, Z-E-N-E, not benzene, Z-I-N-E, that you put into your motor car. And this has a structure of 6 atoms, and of which the atoms in the plane of the molecule they're all filled, and they give the structure of the 6 hexagon. But there is 1 electron per atom, a pi electron, P2pz, perpendicular to the plane of the molecule, that is left over, and that travels around the ring in a bond, in a band of, well, it could have 12 electrons, because there's 6 atoms and up and down spin, but we only have 6 electrons, and so it is a half-filled band, like an alkali metal, and that is what gives it its great stability. Also, the neighbouring atom, I mean the benzene ring, exists in molecules, in all sorts of biological biochemistry. It's all over biochemistry. And so we can think of a benzene with an extra little group added. And that will of course disturb this the 6 electrons and cause a ripple in the electron density of that band, and that oscillates up and down exactly the same way as Jacques Friedel discussed for metals in the 1950s and 60s. If you put an impurity or any change in a metal, it sets up ripples in the electron density with a wave number of twice kF relating to the Fermi surface, and that spreads out. Well, it's the same around the ring if we do something like that to a benzene ring. And these are called the para, meta, and ortho positions around the ring. This part I hadn't really prepared enough. The answer to the puzzles about metallic bonding that I mentioned at the beginning were already implied, but not really thought about and discussed, somewhat hidden in the 1929 by Felix Bloch, the first paper to think of quantum mechanics applied to metals, and it was that paper that created what we now call Bloch functions that spanned the whole metal, and the point about it was it had to assume, in order for the mathematics to work, that it was a perfect crystal extending in all directions to infinity, just pure that metal atom everywhere. Well, of course, that's not the reality, and we showed that I talked about surfaces of metals and hitting them and changing the structure and so on. So this approach that I was using was a more atomic approach, which was started by Professor Jacques Friedel in Paris in the 1960s, where I visited, and it was one of his graduate students, François Siro-Lachmann, who was doing that work. And it was just, yes, it was doing quantum mechanics differently, at least applying it differently to metals. And this was, and I was interested in this, but they didn't. They made some use of it, but not very much, and not in the way that I started to think, with the square root of the coordination number and so on. That then came in the, I think the first time in a review article around 1980, a review article about local methods. And then it's developed gradually since then in my thinking to what was contained in the paper published at the beginning of 2024. Yes. The end.